This lesson is looking at another chi-squared test. This one is a test of independence, or sometimes referred to as a contingency table test. So a contingency table is just a table that looks at things with two variables. One variable is in the rows, the other variable is in the columns. Test of independence is looking at whether those two variables are somehow related or whether they're independent. So on these ones, our null and alternate hypothesis are always the same. The null hypothesis is that they're independent. The alternate hypothesis is that they're not independent. You might notice that's a double negative, so another way we could say that is that they are dependent. So our test statistic is calculated the same way it was with our goodness of fit tests. We take an observed frequency minus an expected frequency, square it, and divide by our expected frequency, add up those totals. What's different is where we get that expected frequency. Also, what's different is how we calculate our degrees of freedom. So our expected value is assuming that these two things are independent, so our null hypothesis. And in that case, our expected frequency for any given cell of our chart is going to be that it equals the row total times the column total divided by the sample size, or another way to say that is the grand total. The other difference, as I mentioned, is our degrees of freedom. Instead of being categories minus 1, because we have two sets of categories, it's actually the first set of categories, our number of rows, minus 1, times our second set of categories, our number of columns, minus 1. Alpha is still the significance level, still typically small values. One thing that's the same as with our goodness of fit test is that these are all going to be right-tailed tests. So, first question, we've got this set of information that says we've got this data about different suppliers and the beams they are supplying. Which one has a higher number of flawed beams that they're getting? So obviously the number of flawed beams is going to be dependent on the total that you get from each supplier. So we wouldn't expect these to be equal, even if they were independent, because we're not getting the same numbers from each supplier. So the values you had in your original question, that's the values in the black that I gave you on your sheet. So that's our expected frequencies. Those expected frequencies are, that's our observed frequencies, FO. Our expected frequencies we calculate from that row total times the column total over the sample size. So what we mean when we say that row total, right, we go across the flawed and we see there's our row total, 174. Column total, 927. And our sample size, that's our grand total, 1500. So in this question, those were all given. Sometimes you're not given the totals, but remember they're just totals, so it's a matter of adding up what we have in each of our cells to get the total for the row or the column respectively. So that may be a step you have to do prior to finding your expected frequency. So I showed that for the first calculation. I just put answers for the subsequent ones. So again, as usual, I suggest you pause the video, do these calculations, make sure you're able to get these numbers and understand where they come from. All of that is just to get our expected frequencies. We still need to figure out chi-squared and the rest of our test. So quick reminder on these ones, the null and alternate are always going to be independent and dependent respectively. So that test statistic that we need to calculate, we're going to need to, for each one of these, take our observed frequency, so in this case 143, subtract our expected frequency, 107.5321, square it, and then divide by 107.5321 again. So on these questions, you do want to keep as many decimals as possible, and we want to keep track of these things. So when I'm writing these questions out, if I'm doing them by hand as opposed to on Excel, we'll also talk about that in a moment, I usually put them so that my calculations are parallel to my table. So this first calculation is like my first cell. Second calculation, second row, second column, I should say. third calculation is this first row, second column, and then this one corresponds to this one, and so on. So that we have that. And then when I do the next part of the calculation, again, these are parallel. So this is my first cell, moving one cell over, moving the next cell over, likewise till I get to that last cell. So I end up with a grand total of 36.47. On the critical value side, we have our degrees of freedom is rows minus 1 times columns minus 1. Well, we have 2 rows and 3 columns. So 2 minus 1 gives us 2, gives us 1. I said that backwards. And 3 minus 1 gives us 2. So it doesn't matter which order we do these in, as long as we have rows times columns, each minus 1. And our alpha on this one was 0.01. So when we look at our chi-squared, 2 degrees of freedom, 0.01 for our alpha. So we're looking at 6.63 for our value. Oh, did I look that up wrong? One of the 2 times I did. Oh, because I did 1 degree of freedom. 2 degrees of freedom. 9.21. And so if we compare that to our test statistic, our critical value much smaller than our test statistic. These are right-tailed, so this is way far into the right tail. So if it's in the tail, in the critical region, we reject the null hypothesis. So these independence tests are always going to come to the conclusion either they're independent or they're dependent. So if we're rejecting that they're independent, we're supporting that they're dependent. So there is enough evidence to reject the claim that it's independent. So some companies are having a higher rate of defective beams. You can see how that might be a useful thing to know. One thing I would point out on these questions, actually 2 things. First thing I would point out is that sometimes there's a shortcut. If you calculate the critical value first, all we really need to know is that the test statistic is larger than the critical value. And in this particular question, we would have had a shortcut because when you calculated the first of all these 6 values, it was already more than 9.21. So we can see that that test statistic, even from that point, without calculating the other 5, we can see already that it's going to be in the critical region. So we could just say the test statistic is greater than the critical value and jump to the conclusion. The other thing I would point out on these is this is a really long repetitive calculation. And we have a tool for long repetitive calculations. It's called Excel. So if we look at the same question in Excel, let me bump up the size there so it's a little easier to see. So if we look at that in Excel, we again still start out with these given values. If you needed to calculate your sums, you can definitely use the sum function on Excel. But we can use Excel to calculate those expected values. So you'll notice what I did here. I did use some absolute value functions so that I could copy and paste that. Right, so I'm looking at my row total, column total as I paste over. The thing that's changing, right, is that column total. So then when I went over to the next cell, that changed, but the other one didn't, right, my one in red. So I was able to take that and copy and paste over and then do the same thing in the second row. So when we do the calculation for the test statistic, and I just embedded the equation there, so that's floating on top, I can move it around, it's not in a cell. So when we do that calculation, we're taking these values for our observed and we're taking these values for our expected, so we can do the calculation, right? Observed minus expected squared divided by expected. Since I'm repeating that over and over again, I can just take that calculation, copy, paste it over, and I can keep as many decimals as I want, right? So I've shown this with quite a few decimals. And then we can have our test test statistic, can't talk. Test statistic is the sum of all of those values. So Excel is very handy in these because it does do those repetitive calculations for us. So the next example I'm going to show with Excel as well. Given that this will be an online test, Excel is an option open to you even during the test situations. So our critical value from the table, but Excel does have a chi-squared function. So just like our normal distribution function, if we want to look at the inverse or the Poisson or the binomial, chi-squared is the same thing. So we have chi-squared inverse, and then the RT is referring to the right tail, and then we need to use our alpha. So in this case our alpha was 0.01. That's our probability. And lastly, we put in our degrees of freedom. So we can get Excel to calculate that as well, and it'll do it to more decimal places than our table if we should end up in a situation where it's kind of close. So that is also a handy piece of information to use. Okay, going back to our second example. So we have a dean of a business school looking at MBA courses and majors, and the question is the major chosen related to the undergrad degree, right? So are these dependent or independent? So again, first table is our given information. I did the expected values as a separate table. Well, where did I get these values from? I said, let's go straight to Excel. So I took this whole thing, copied it, and pasted it into Excel. So we have that table, right? And I can't remember, did I give you totals? Yes, I gave you totals. Have that table, and we want to figure out those expected values. So for this first one, right, we want row, whoops, didn't mean to click on there, row times column divided by our grand total. Same thing as we move across to the next question. Row times column divided by the grand total. So we're getting these expected value, calculation for each of these. Once we have all those expected values, again, we can do that repetitive calculation of observed minus expected squared over expected. So here's all my observed, here's all my expected. So if I'm doing this by hand, right, this is a 3x4 table. I've got 12 of these calculations to do. So it does get pretty repetitive, and Excel is very handy. So again, we can check those values all are coming from those two tables, and then we can add up a total to find our test stat. So this one, these were all pretty small. It was fairly close to the expected values, right? None of them were hugely different. Whereas in the previous question, since I've got it up here, right, we had some that had 143 versus 107. That's a pretty big difference from what we are expecting if they're independent. So Bose beams is giving us more than expected. Here, they're all pretty close, so we actually do need that total to compare to our critical value. I'm just going to go back to the Word to talk about that critical value with the table. But our, as we can see on here, our alpha, 0.05, where our 6 is coming from, remember that's our degrees of freedom. So we have a table that's 3x4, so remember we subtract 1 from each of that when we calculate our degrees of freedom. So 2x3 gives us 6 degrees of freedom. So if we go back to, that is not what I wanted to go back to, this one. If we go back to our chi-squared distribution, 6 degrees of freedom at a 5% significance level, right, we can see that that's 12.6. And again, I had more on the Excel sheet because Excel's handy that way. So null hypothesis, independent, alternate hypothesis, not dependent, not independent. Did our calculations, and again I showed them here. critical value test statistic. So our test statistic is right of the critical value. There is enough evidence to reject the claim that they're independent. Again, we could also say it the other way around. We could support the claim that they're dependent. So that's our examples on doing tests of dependency using chi-squared.